This lesson is half lab, half notes on magnetism. This is a piece of magnetite. It's got a little sticker on it. It's a naturally magnetic rock, first found in Magnesia in Greece, and that's why they called it a magnet. And it is naturally magnetic. It has just enough magnetism to just barely attract this little paper clip. Not quite lift it, but enough to attract it. It's a little easier to see if we use a compass. A compass has a magnetic end that points towards north. When we get a piece of magnetite near it, notice that this magnetic rock messes up the direction the compass is pointing. You'll see that a stronger magnet has much greater effect on this compass. In fact, it can even turn it completely a different way than it should be. Here's how to use a compass. First, let it settle. The red painted tip points north. So spin your compass until the letter N lines up with the red tip. Once the painted end of the pointer and the letter N are both facing the same direction, then you'll know that that way is north. The opposite way is south, east, and west. And if you forget which order they go in, never eat soggy waffles. The ends of a magnet are called the poles. It has a north pole and a south pole. But why is that? Well, just like this compass that we just looked at, this magnet will act like a compass. I'm going to draw a few little arrows so we can remember which way the compass was pointing. I've got a paper clip and I've made a little hook out of it and attached a string, and I'll place a magnet inside this little hook and hang it from the string. And I'll wait until this finishes spinning, and if you'll notice, it's going to line up just like the compass did. So this lines up the exact same way, with the north pole of the magnet facing north and the south pole of the magnet facing south. That's why it's called the North Pole, because it's attracted to the North Pole, and it always points north. If I hold this magnet up, pointing north, and I spin, you'll notice the magnet continues to point north. See, there's the north on the magnet. And even though I completely spin around, the magnet still points north. There's the north and there's the south. I must have some cheap compasses, because you'll notice only one does the red pointed end point north like it's supposed to. The rest of them, they painted the south end red, and that's wrong. Now, the magnetic field is the region around the magnet that's affected by the magnet. Let me show you what I mean. Here we have some iron filings in a bag. That means somebody took a file and scraped it against the iron until the little chips of iron fell off. And those are iron filings. When we shake the iron filings over the magnet, see how it lines up with the magnetic field? Let's try that again. It's messed up. We put it over the magnet, and looky there. See the pattern that it makes? So this is the pattern that a magnetic field makes. You'll notice that it comes close together at the north and south poles and spreads out further around the magnet, just like the pattern that the iron filings made around the magnet. So the iron filings show the magnetic field lines and where they are, because of course they're invisible. The field lines are closest together where the magnet is strongest. So see where all the lines come very close together? That means the magnet is strongest at the poles, at the South Pole and the North Pole. It's not as strong in the middle. So I've taped down two magnets with the north poles facing each other. Now let's see what happens to the magnetic field. Use your iron filings and shake them over the two magnets. Well, looky there. Notice the two magnets are repelled from each other and there are no little pieces of iron filings in the middle. See, they just go away. That gives us a magnetic field that looks like this. Now let's tape the magnets with the opposite poles facing each other, north and south. Use your iron filings. This time they're attracted in between the two magnets and fill up the space between them, which gives you a magnetic field that looks like this. So this shows you the opposite poles of a magnet attract and like poles or the same poles repel. So what causes magnetism? In a ferrous or iron material, clusters of atoms align themselves with one another. A cluster of billions of atoms with their magnetic fields lined up the same direction, is called a domain. When the domains are randomly arranged, like you see here, the material is not magnetic. Everything's just jumbled up. But when the domains are aligned or lined up together, the material is magnetic. What happens when you snap a magnet in half? You'll notice this magnet has already been broken. So I decided to use it for this problem. The South Pole is still a South Pole because it's attracted to a north and repelled from a south. But what about the other end of the magnet? What has happened to it? Well, it doesn't like a North Pole, and it does like a South Pole. So this broken end has become a North Pole, while this south end has remained a South Pole. What happened was all the little domains inside the magnet remain lined up. So the ones on the right are still a South Pole, and the ones on the left are still a North Pole. Then, what about this end? The North Pole is still a North Pole because it's attracted to a South Pole. And the other end is a South Pole because it's attracted to a North Pole. So this has also become another magnet. So when you break a magnet, you end up with two magnets because the domains remain aligned. Go ahead and label your magnet. Label this end north and the broken end south. Label this end south and the broken end north. So how do you destroy a magnet? Well, you notice that magnets get weaker over time, especially refrigerator magnets. And that's usually because they've been dropped over time. Every time you drop a magnet, you jumble up these domains and it becomes less magnetic. So you can drop them or you can hit them hard and that will do the same thing. They will cause the domains to misalign. Heating or melting will also cause the atoms to vibrate faster and faster and once again will misalign the domains. So it's pretty easy to mess up a magnet, but how do you make one in the first place? This paperclip is just barely magnetic. See how it turns the compass just a little bit? This is a very strong magnet known as a neodymium magnet. It's really hard to get apart and they stick together super easily. So the way you turn this paperclip into a magnet is to drag the strong magnet across the paperclip. Notice I'm always going in the same direction every time. If I pick two different directions, I'll misalign the domains. But now that I've magnetized the paperclip, look at how strong of a magnet it is. It can completely spin this around. It's just barely strong enough to lift another paperclip just a little bit, but not much. Once again, notice how strongly the compass is attracted to it. Now I'm going to take a hammer and hit the paperclip. What do you think will happen when this paperclip is brought near the compass? If you'll notice, the compass is still attracted to the paperclip, but not nearly as much as before. I can't get it to spin completely around like I used to. If I would continue hitting this paperclip with a hammer, I could demagnetize it even more. When I test it against another paperclip, it's now nowhere near strong enough to lift it. Another way to make a magnet is to use electricity. We'll learn about this tomorrow. A temporary magnet is made from materials that become magnetized while in contact with a strong magnet. For example, this paperclip itself is not magnetic. However, when I attach it to a magnet, it becomes magnetic. See how it's easily able to pick up the other paperclip? Then, when I remove it from the magnet once again, there's still some residual magnetism, but it's not nearly as strong as before. And eventually, the magnetism will go away. So this is a temporary magnet. An electromagnet is also a temporary magnet. It's only magnetic when electricity is flowing through it. Temporary magnets only remain magnetized for a short time, and then they go back to being non-magnetic. But permanent magnets are made from materials that retain or keep their magnetism when the magnet is removed from them. This is a permanent magnet. It's magnetic even if you remove a strong magnet from it. However, as you've just learned, permanent magnets are not magnetic forever. They're just magnetic for a long time. Remember, you can always demagnetize them by hitting, heating, or dropping them. Let's test out some different metals to see if they're magnetic or not. We have zinc, iron, aluminum, and copper. Not magnetic, definitely magnetic, not magnetic, not magnetic. In fact, only 3 metals are attracted to a magnet. They are iron, nickel, and cobalt. Steel is also magnetic, but only because it's made of iron. So, sorry, if you lose your gold or silver jewelry, you can't find it with a magnet. Speaking of magnetic materials, it turns out that Earth's core is made of swirling liquid iron. That iron makes the entire Earth one giant magnet. Therefore, even the Earth has magnetic field lines. Remember, Earth is tilted slightly instead of straight up and down, so its magnetic field is tilted as well. The Earth's magnetic field protects us from the solar wind, or cosmic rays. These are high-energy rays that could damage living things. When the Earth's magnetic field interacts with these cosmic rays, we see the aurora borealis, or the northern lights. Here's how that works. When the solar wind, or the cosmic rays, hit our Earth, the magnetosphere, the Earth's magnetic field, distorts and helps to push the solar wind away from the Earth. Then you'll often see a ring of blue, green, or pink at the North or the South Pole as the stronger magnetic field near the poles interacts with the solar wind. And now I believe you'll be able to answer the rest of these questions on your own.